Seminar from the Psych-Eng collaboration, the Psych-Eng seminar series, and also the new Research and Focus seminar series that the Mechanical and Industrial Engineering Department is putting on. Professor Gero is here. He's a professor in computer science and architecture at the University of North Carolina at Charlotte and at the Krasnow Institute for Advanced Study at George Mason University. He's the author of 50 books in over 650 papers and chapters in the fields of design science, design computing, artificial intelligence, computer-aided design, design cognition, and cognitive science. So a real breadth of topics. John has also been a visiting professor at a huge number of universities: MIT, Berkeley, UCLA, Columbia, Strathclyde, EPFL, and more. I just took a limited number there. And so Professor Shu and I, who are co-hosting John, saw him speak at the American Society of Mechanical Engineers International Design Conference at the end of August. And we found this work to be really interesting, and we're very glad that John was able to come to Toronto, to the University of Toronto, to share this talk with all of you. So thank you, John. And,
I always like it when you clap before the talk, because there's no guarantee that afterwards. But anyway, what I want to do is, I was told this is what, 2 hours? No? I want to introduce you to things that normally as engineers we don't even think about, to our peril. We think engineering is about manipulating materials, particularly if you're in the head of the materials department. And we forget that we're actually human beings. I took a sociology class as an undergraduate, and my sociology professor says the trouble with engineers is they think humans are like things, and they can be pushed around and shaped. And as you probably know, that's just not true. So, what I want to do is to introduce you, maybe you know all this, in which case, play around, to the notions that we have minds and brains. The two are different. I don't know what the difference is, but we all know somehow what the difference is. You know, the brain is the stuff that you can poke, and something happens when you poke it, and the mind is something you can't poke with your finger, but it turns out to be really important. It may be an artifact, but except we can measure the mind. So what is in the mind? The mind is the place where we think our thoughts occur, and the mechanisms are in the brain. And we can measure things about the mind, and the field that does that is called cognitive science. And it's an amazing field. You can measure things and get repeatable measures, good scientific work, the stuff you can't see. Of course, as engineers, we're familiar with this. Most of the stuff we play around with, you can't see either. Right? Talk about anything outside the visible spectrum you can't see. So it shouldn't come as a surprise. The brain, however, we can see. The trouble with looking inside the brain is you don't see anything about what you're doing. It's sort of like looking inside a computer. If you look inside the, say, the CPU of a computer, what you see running around are electrons. And all the computers have electrons running around in them. It's the quantum computers a little bit different. Biological computers, but you know what I mean. And it doesn't tell you that I'm doing, pro-engineer, and I'm writing a letter to my best friend, or I'm watching Netflix. All looks the same. So it turns out there's something else going on. That's sort of the duality between mind and brain. And the talk I gave, wherever that was, I go, where was it?
Quebec, Quebec City.
Oh, yes.
Yeah.
So I've been to a lot of places since then. Was a little bit more narrowly focused because I didn't get 2 hours. where we were interested to see, since we teach different design methods, does that actually do anything to you? Or is this just us, standing up, you guys sitting there, which by the way is a really bad educational model, and I hope we don't get too much of this except when I'm around. Does it actually affect you? That's what this is about. Okay? So, one of the ways we study the mind is through the behaviors that are generated by the mind. And one of the behaviors is the things we can see through our senses or through tools that allow us to sense things that we can't see. And most of the things that when we, as human beings, interact with each other, say, is through utterances, voice, just as I'm doing now, except this is sort of one way. But it's very clear that when we listen to things, something happens to us. And there's a field in cognitive science called protocol analysis, which is data from verbal utterances. That's precisely what it is. The field's been around for 50 or 60 years, but it's become much more sophisticated. So, what does this look like? We can do experiments, or we can do in laboratories, or we can do them in situ, in people's offices and so on. And what we do is we either give people design tasks and listen to them as they produce designs, watch what they do and videotape what they do and what's on as they draw it, whatever way they describe it. Or we go into their offices. This one here, for example, it's blurred intentionally. This is an industrial environment with a design group. We put up 4 cameras and walked away. And just then listened to them afterwards. This is people in different places around the world trying to work together. So what protocol analysis does is it listens to people, we convert it into a transcript, and then we break it up into, the technical term is either moves or design issues, which means we segment it, so we have a chronological segmentation, and we take a language, and I use the word language in a formal sense, in order to code up by what is happening there. So, for example, are they talking about, this is a crude language, are they talking about the problem, or are they talking about the solution? So that would be a 2-word language that already abstracts out where the guy is actually talking about gear teeth or talking about marketing. These are 2 different things, but they can be abstracted out. And we use a language to convert this sequence of utterances into segments which are coded, and now we end up with a string, technical term if you want, in a language. And we can do all sorts of things and build statistical models of the behavior of the mind. That's what we do here. So, here's an example of studying what happens when undergraduate mechanical engineers start off in their freshman year and then choose majors. And the 2 majors we've got here, ME is for people who do mechanical engineering, which involves design. This is Virginia Tech, and this is work done Chris Williams at Virginia Tech. EM are for people who do engineering mechanics, which means that they get involved in applied math. And what this measures is the change in behavior between their freshman year and their junior year, where they've had this bifurcation. And this is the verbal description of the language that is used. And it doesn't actually matter too much what it is, but rather what's interesting is how we can now measure the differences that occur. And we can do statistics on it. So visually you can see this thing here, where there's big changes. All right, we lost it. The blue are the mechanical engineers who did design, and the red are the also mechanical engineer, but who got it removed into engineering mechanics. And what we can see here is this thing here is what we might call something associated with analysis. That is, what's the behavior of the thing you produced. And this confirms our hypothesis that people who do engineering mechanics then put whatever they see in front of them, they're going to try and work out what's its behavior. Whereas people doing mechanical engineering design, when they see the same thing, they put less effort into behavior, less effort into analysis. And what we see, something which is really also interesting, is people doing engineering design are taught to draw this stuff out, to represent it. Now, these are things we know, okay? But now we're measuring it, and we can look at the effects of, say, this is part of a story on looking at the effects of different kinds of teaching. Can we accelerate change and so on? So this is what cognitive science used to study design, which is called design cognition, can give you. It can give you amazing stuff. I mean, here's a nice, simple example. This is work done with Tom Sakau in Sweden, although the people we're studying are in Japan, but that's all right. Doing product service system. It's not exactly the color. Product service system design. As you know, increasingly, I'm sorry if you're going to spend all your life doing machines, but that part of it's getting smaller and smaller in the world, because machines turn out to be only part of a story. Increasingly, they're part of a service that's provided. And the service is not machines at all. It's something else, generally much more intangible. Anyway, so this is studying product service system designers, but taking our language, which had 6 words in it, and just allocating them into 2 bags. One bag says this is about the problem, and the other one is about the solution. And how do these designers distribute their cognitive effort over time between these 2? Theory, and the way we teach, says you should look at the problem, analyze it, work it out, look at what the variables are, the dependent, independent variables, and then start to build what kind of things you're looking for. When you look at what people do, red is the solution. You discover they put down ideas almost immediately, and then start to think about the problem a bit more. So, is theory wrong? Is practice wrong? I don't know. But there's a mismatch here between what we teach people and what they do. Or maybe it's just in product service systems. So this is part of a bigger project which looks at that. But what I want to talk about is not that. I want to talk about a project looking at what happens if we teach you different, to be precise about it, concept generation techniques. How to help you come up with ideas. Because studies have shown if we just say, give me 10 ideas, you struggle. But if I say, look, here's a way of producing ideas, you do better. And there's many, 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 many ways. There's a beautiful book whose name I've forgotten a little bit, but it's something like 101 Universal Design Methods. And it's pretty good. It's not just prescriptive. It's not just do A, B, C, and then you'll end up with a load of money or something. It gives you the ideas behind it. So that's what we were interested in. So we took 3 design methods. Brainstorming, which everyone thinks they know, but brainstorming is not what you think it is. It may be. Brainstorming is a formalized method of putting ideas down without testing them. There's no testing. And when you sit in a group, no one can say, well, that's not going to work. Brainstorming is a sort of pseudo-structure about idea generation, concept generation. Is morphological analysis, does that mean anything to people? To you? How about anyone? I presume sitting there like this means no. That's okay. Bit of a shame, but that's okay. You should talk to your professors. It's another method. It's much more structured. Much more structured. Based, I'm not going to tell you what it is. You will have to pay me to give those lectures. And I'm not being paid. I want you to know. And then the third one is TRIZ, and I'm told you some people know about TRIZ. But the interesting thing about TRIZ is, which you may know, but I'm going to tell you anyway, because I'm a great believer in having a broader view of the world. TRIZ is the only design method to come out of the Soviet Union that is used by anybody at all. And it's used quite extensively in the motor car industry in North America. Quite surprising, but not surprising when you look at it. It's a highly structured method that has become richer over time, and there's a whole community around it, presumably because it does something for you. It's not just marketing. Right? So these are the 3 methods that we teach people, amongst others, and we thought, let's see what happens to their minds and their brains when we teach them. Does it make any difference? So if it doesn't, you've got to ask yourself some questions. So here we go. Well, not too well, but okay. Across the horizontal axis is time. By the way, I have beautiful graphics here. We've divided, so this is the result of, 15 or 20 students. These are at Virginia Tech. And we've taught them brainstorming, give them a tutorial, give them an exercise. We measure the exercise. We teach them morphological analysis, which I notice has disappeared, but sits in between these 2 lines. We teach morphological analysis, then we do tutorials, give them an exercise, which we measure. And the same with TRIZ. What's the vertical axis? The vertical axis is something called the VS index. And what it measures is the ratio of the cognitive effort spent on the problem to the cognitive effort spent on the solution. Okay? That's a non-dimensional term, so we don't have to worry about what cognitive effort means dimension. Right? The higher it is, it means the more effort you spend on the problem. And the lower it is,
Sorry.
you think there's a better.
But this looks so.
It is, but much. Let's not confuse the thing with what we're talking about. That's all right. Listen to me. So, the higher that number is, the more of your effort goes into the problem, thinking about it, working on the problem part before you head to the solution. And the important thing here, big differences in behavior at the beginning. And then towards the end, they all sort of look the same. Now, this kind of behavior, as opposed to its values, that is, this signature, graph signature that looks like this, is observed all over the place when people design. We study, I mean, these happen to be mechanical engineers, but we study civil engineers, we study architects, industrial designers, we study curriculum developers, software designers, hardware designers. Everyone sort of looks like that. The difference is only in scale, magnitude. But that's important because once you get over one, whatever that is there, it means more of your efforts going into the problem than into the solution. Now, I have really interesting slides that I'm not going to show you about the difference between mechanical engineers and I think I'm not going to show you, and industrial designers, because I don't want to talk about that. And if you're a mechanical engineer, and I don't know what happens in this school, you don't look so good. And it's not because of you, it's because of your professors. Because you're taught in a way that I'm going to stop there. we can talk about that later. So, we can measure the mind, and we're quite sophisticated about it. I mean, we can do things that you couldn't imagine. It's a different talk, but I can tell you, you all know what entropy is, right? Because you've done thermodynamics. Have you come across information entropy? Does that mean anything? Well, that's a real shame. You shouldn't necessarily. But anyway, we can tell you about the, not the thermodynamic entropy of your mind, but the information entropy of your mind, which is a very, very sophisticated idea. Now, how do we measure the brain without cutting you open? And actually, cutting you open doesn't do it, which is really fortunate, right? Because otherwise we'd have these ethical problems. These are all non-invasive techniques, and the famous and the important ones, the one you've probably heard of, is this thing, fMRI, functional magnetoresonance imaging. How do we get it? What that does is it measures blood flow. Actually, it measures the water flow in the blood. Based on a very simple idea. In all blooded organisms, energy is carried by the blood, and the body takes blood to where it's needed. And whether it's in the brain or whether it's in your finger, it transports blood. The more it's needed, the more the blood flows there. So we look for blood oxygen demand and correlate that with cognitive activity. So if you're thinking about something in a region of your brain, we will see more blood flow. That's what it does. The problem with this fMRI is you have to lie still. That's okay. If you've got a medical problem, you're very happy to lie still if you think someone's going to help you. If you're trying to design something, lying still is really hard, on top of which most people use their hands, they want to draw, so it's not such a good environment. Plus, it's slow. Has anyone here ever had an MRI? Okay, I've had an MRI, unfortunately. It's very noisy, and it takes a while, and it does what it does do is it builds this beautiful 3D model of your brain after you've done 20 minutes of computation. Right? Those beautiful pictures don't just come out like this. There's a lot of manipulation. So it's not so good, because designing is a temporal activity. It takes time. So people came up, probably independent ones, came up with how to measure electrical signals in the surface of the brain. Nothing to do with blood oxygen demand at all. Measures just that. EEG. But there seems to also to be a correlation between electrical signal activity, total response, the amplitude, and what's happening below it. So we have another way. The advantage of EEG is that it's temporal. Its resolution is not so good with geographic resolution. And there's a relatively new method which is called functional near-infrared spectroscopy, for NIRS or FNIRS. And what it does is it shoots an infrared beam into your brain and measures the reflected beam and looks at the spectral distribution and what's absorbed and gives us an indication of blood flow again. The advantage of this is, A, you don't have to be stuck in a $1 million machine. You can move around. And it's temporal. The current, depending on what machine you buy, runs between 7 and 20 hertz. So these are so that's really good for us. So I'm going to show you some results of doing this. And I'm just going to show you initially some EEG studies of, in this case, mechanical engineers and industrial designers. So this is brain behavior. I didn't show you the cognitive behavior, right? This is the device we used. You can buy this for $700, anyone can buy this for $799 US, I don't know, what is that, 2,000 Canadian dollars? Sits on here, not a device you do neuroscience with, right? It's a device you do design science with. Its resolution is not that of that kind of experiment. And let me tell you the experiment we've shown here. I'm going to show you the results of it. We start off by getting people to do what is called a pre-test, which in itself doesn't have much to do with the thing we want, when it's connected to it, to give us some indication, so we have a base there. And then we give you a very tightly constrained problem, for which there's a very small number of solutions. And we don't think of that as a design problem, except in some extreme sense. And then we measure brain activity. So this is EEG. Measure brain activity, and we make that the baseline. So we set that at 0. Everything will be later to that. We give you the same problem, but with fewer constraints. We do the same problem again with even fewer constraints, then we give you an unconstrained problem. That's what we're going to see. So, what have we got? The orange is experiment, is task 1, and that's our base. Right? Task 2 is the grey. What are these things? These are what are called channels, and they're geographically distributed over the brain. So these two are not necessarily next to each other in the same way, but these two are next to each other. There's an international standard for how you distribute this, so anyone who's doing this work knows where these are. The yellow one is the third class, and the fourth is the sort of unconstrained class. And what we can see here is that we have differences, and of course we can measure differences statistically. The different parts of the brain are activated for different kinds of tasks. Something else is very interesting. Look at the level of activation between industrial designers and mechanical engineers. And there's significant, and I mean in a statistical sense, significant differences. And this provides more evidence for stuff that we see between industrial designers and mechanical engineers' cognition. Mechanical engineers are taught to bring problems down to what they know. Because the knowledge base in mechanical engineering is really strong. It's based on physics, applied physics, electronics, just physics, right? Of course, the boundary gets bigger and bigger. Nano stuff. Industrial designers don't have a strong knowledge base, so they can go anywhere. And when you look at we've got cognitive differences, we have brain differences, and when we measure what they design, the output, we also get big differences. So if you want a truly innovative, let's say, consumer product, don't go to a mechanical engineer. Don't go to a traditional mechanical engineer. Perhaps that's what I should say. That's not true. Because we're individuals, right? Yes.
If we're already sort of at the end of the mechanical engineering program,
You have to.
if we're already at the end of the mechanical engineering program, how would you suggest tips on doing that type of
Let's leave that. Because I want to finish this first, okay? But it's a truly good question. I'm just trying to work out how much to charge you for the answer. So, clearly there's something happening here. Because now, and what's happening is, first, we have a lot more knowledge than we ever had before. This was all, if anyone thought about it, it was total speculation. Now, be careful. I'm making these provocative statements because I want to be provocative. This is the result of testing 100 people, not 1,000 or 10,000. Scientifically, that's a good number. In practice, it's not. Right? All of these people are Portuguese. I have a group in Portugal that does this. We haven't done this for people, say, from differences. We found differences when we test Chinese students against North American students. Not big differences. Now, I want to show you this functional infrared spectroscopy. And the way it works, as I said, shines a light, you get reflection, and it does some massaging, and it tells you how much blood flow there is. And what it looks for is this area under the curve. This is time. This is the blood oxygen demand. So it's the blood oxygen level dependent demand. And that's what we're measuring. And there's good correlations between that and actually what's happening in neurons. And the way we do this, just because you're engineers, you should have no trouble with this. Here we are, we measure this for different channels. So these channels are distributed across the prefrontal cortex, which is this part of the brain, maybe up to here. Two halves, left hemisphere, right hemisphere, which refers to the whole brain, and this is just the prefrontal cortex, or the dorsolateral prefrontal cortex, which is back here. Because that's the last part of the brain to develop. I don't mean in people, I mean in an evolutionary sense. And that's where decision making and all that stuff goes on. The rest of the brain is full of really important things that we use. Color recognition, edge recognition. Memory is it's all over the place. Memory is not like in a computer where you can point to it. Spatial understanding is back here in the hippocampus. The brain is, the more we know, it turns out the less we know. We're just uncovering more and more. But we know enough. So what this is we look at every channel and look for temporal-based correlations. Is this activated when this is activated? And that gives us, tells us something that's not black, but it doesn't matter. We can get networks, and we can measure things about the networks. let's have a look at what we did. So, that doesn't matter, we covered all that. This is actually what it looks like. We make people wear these little red, that's not true. That's so you don't know who they are. And then this is what it sort of looks like. This is the result of a dozen graduate students in mechanical engineering, in civil engineering at Virginia Tech, not mechanical engineering. And this is the first interesting result. Well, the other's really interesting. This is the behavior of brain activations just across the brain, prefrontal cortex, across time, while you're brainstorming. And this is for a lot of people. Right? And what we see is exactly what we expect, which is that over time, there's less activation. Your brain just moves on, even when you're trying, right? Because we're really bad at what is called self-regulation. But we know that humans can self-regulate remarkably. And two types of places where we know this. There are people in India who can, by thinking, regulate their heart rate and their oxygen demand to way below what we believe is necessary to sustain life. And it's done by self-regulation. There's also, in medicine, feedback mechanisms that they use. Right? So we know we can do it, but we don't know how to do it. Okay. So, and now we can compare the brain behavior for these three different methods. It's the same sort of experiment. These happen to be civil engineers. We get actually statistically the same result from mechanical engineers. And what's interesting here is brainstorming, and we're looking at activated networks. What does that mean? Different parts of the brain correlate in that they're being activated at the same time. And we build a network from that. Right hemisphere doesn't mean the whole brain, it just means this part of the brain, the part that sort of sits here. Morphological analysis is over here. It's so much for left brain, right brain. You know, this is the creative part, and this is the analytic part. I don't know, not that simple, it turns out. And trees involves more of the brain. So physiologically, we are quite different when we're doing these different things. That's an amazing thing to be able to say, right? That really, now just think about it. This impenetrable thing that we can't introspect into, we can tell you about. And this can be generated in near real time, not like something that, well, increasingly with good computers. So we can actually see this happening. So, and this is just showing you where these networks are, what the dominant networks are. Actually, I thought because we're engineers we should do more about network theory, but actually it's not very interesting. If you're interested, there's a lot to say. We find significant statistical differences across these three methods. So it's not just, we see it. Every place we look, we see these differences. So, what is it telling us? Really big brain behavior differences. And the brainstorming is lower than morphological analysis and TRIZ in the cognitive effort put in. What we haven't got to, with this experiment, although with other experiments in the cognitive domain we have, brainstorming is one of the weakest methods for producing, let's just be loose and say novel results. Unless you don't know much. There's this really unexpected inversion. The less you know, up to a point, the more novel your ideas are, because you don't know that some of those things people say don't work, even when they're wrong in saying that. Really interesting. When we study novices and experts and get their ideas assessed by experts, experts always come lower on the creativity scale than novices. That's part of the answer for you. Don't know too much. No, that's not the answer. You've got to know what to do. So, really important things here. Our brain behavior matches our cognitive behavior. No necessary reason for that. I mean, obviously it should, but should isn't the same as does, right? Professors should get paid much more than they do, no question, right? But they don't. So should, you've got to be careful about that. What's interesting is that cognitive behavior is an artifact. We don't know what's in there. Brain behavior is much more objective. Everyone gets sort of the same result. Actually, they get the same result probably as well. You can't see it, you can't touch it, people get that.
We only have a few more minutes, 6 or 7 minutes.
Oh, okay.
Yeah.
I forgot about that. So, I want to finish with this. What sort of things can you do studying the brain? Let's look at this. This is this device. This person is thinking Zoom. The system tracks his brain behavior, does some learning over it, connects it to the CAD model Zoom, and now all he's doing is thinking Zoom. No touching, no words. The system zooms. There's a new world out there as we know more about the brain. I'm not going to show you that, but it's just another one. Cool. Where are we up to? I just want to finish here. So, what does this tell us? As we know more, we discover there's more we could know. What we're taught is always the past. It's really hard to teach at the present, and you can't teach the future. But if you think the world finishes with what's in textbooks, you're in the wrong place. And let me finish there. We have time for some penetrating questions. Yes?
Yes.
You have to speak really loud in the acoustics.
Yeah, so I come from a mechanical engineering background. So first of all, I don't believe this. Second, one thing is that does it depend on the design task that you give the industrial engineering and the industrial engineering people and mechanical. For instance, they have background in this, that's why they think differently. That's the first question. The second question, thinking about the problem doesn't mean that you're going to solve it at the end. You're just thinking about it, right?
Yep.
So who solved it at the very end? And does that, how can you measure that?
Okay. The first one, if you give people tasks that involve very low domain knowledge, but some domain knowledge, mechanical engineers and industrial designers look pretty much the same. Where there become big differences is where there's very little knowledge. Industrial designers wander all over the place, and mechanical engineers don't. And there's good reasons for that behavior. because mechanical engineering in general deals with a world where there's bigger risks. I don't want the plane I'm on, or anyone is on, to fall out of the sky, right? On the other hand, if this thing doesn't work properly, which it doesn't, by the way, I just say, why didn't they do a better job? I don't fall out of the sky and die. So of course you don't want mechanical engineers to be like industrial designers, but it doesn't mean you can't learn. And I'm only going to take one question from anybody. Next question. Yes.
During your study,
You have to shout. It's either I have bad ears or the
No, it's better.
acoustics is bad.
During your study for the different concept generations, different tasks were assigned for each type of concept generation. Would it be different if those 3 types of concept generations were used for the same task? Like, I was wondering, why did you, during the course of the study, why did you decide to choose task 1, task 2, task 3, and apply the different?
Okay. These tasks were sort of tested in the best way we can for being functionally similar. That is, the kind of knowledge that's needed, the kind of complexity, and the description of the task is the same. We've actually done them in random order. You get slightly different results, I should say, but the result is the same. Yes?
What, so with the FNIRS, is that how you say it, FNIRS? Are you going to stick with concept generation studies, or is there another part of design that intrigues you to pursue with this new technology?
Okay. The question was, are we going to stick with concept generation? And the answer is yes and no. We're going to stick with concept generation. We're going to expand it to judgment. Because that you produce something, but you also have to assess it. And we know that students are really bad at judgment. So we've got a funding proposal in to compare professional engineers, the 10,000 hours type engineers, with, I think, master students, right? To see that difference. We're in concept generation and assessing their concepts. So that part. So these are like the 2 ends of the design spectrum. Yes?
I was wondering if you had finished the thought that you began earlier about what engineering students are taught that is wrong. The thing
Okay. Let me answer that quite seriously. What they're taught that I believe is wrong is not what they're taught out of textbooks. I don't think there's anything wrong with what's in the textbooks. What I think they're taught about, and I wouldn't use the word wrong, I would use I might have said that.
well, maybe not.
Yeah. Is incomplete, is that the world doesn't finish there. And that deploying knowledge is as valuable as that knowing knowledge, actually more valuable. Knowing what to use, when to use it, and when not to use it. And we don't exercise that part of it at all. Particularly when we give, I don't know, you call them P sets here, problem sets, and we give people problems as if, we're telling you about the world, right? Tell me about, what's the thermal distribution of this thing as it runs through hyperspace. Good thing to work out, right? No question. But what we haven't said to anybody is, how did you even get there? I mean, really, why are you bothered about the thermal distribution? Here we're doing it because we want you to understand thermal distribution. Nothing to do about what's happening in the world. And we have very little about judgment because the answer's there for us. You don't get it right, well, you go and talk to people. But that's not the way it works. Your answer in practice can change everything. Can change the ways in which you assess things. You decide to bring in, carbon fiber materials. You don't test carbon fiber materials on exactly the way we test concrete. You need some new things. And that's where I think we're weak. We're incomplete. We teach backwards only.
I think we have just time for one more question.
Do you think there will be some type of learning effect for the cognitive effort for people using topological analysis or TRIZ, because if someone's using brainstorming, they'll have to, everyone knows what brainstorming is, so they have to use common effort to try to understand that concept generation method. But if you give someone a problem and tell them to use TRIZ, you might be putting effort into like trying to think about what TRIZ is rather than actually putting effort into the problem or the solution. So it's a way to.
The answer is yes, but we've tried it in other directions, right? And then we get similar results. Not the same at all.
Okay. Thank you, everybody. Thank you, Professor Gero.